So let's start. As I was trying to explain that I've already uploaded a few things in our classroom. This is the actual specification provided by the Pearson Edexcel website, but it has like everything in detail and it really doesn't talk about the topics that we are going to discuss in our A2 syllabus, right? They only like list out the formula, like few of the formulas and doesn't have everything in detail, like what are the topics that we're actually going to study in our A2 syllabus. I mean, they have core practicals listed over here, but other than that, the subtopics from every main topic are not included in this. So that's why we are going to like give you a list of all the topics that I will be explaining in one chapter. For example, this is the momentum topic list. This kind of list will be uploaded at the beginning of every new chapter. So these are the subtopics or important things that we will be considering solving in our momentum calculations. So for linear equations, that if you focus on this one, I don't know if I can zoom in here. Okay, so if you focus in this one, the momentum is broken down into two subunits, linear momentum and angular momentum. There are obviously a lot of things you can clearly see, like bullet points, like 7 to 8 bullet points under the linear momentum concept. But for angular momentum, that doesn't have anything. Like if you understand the concepts for linear momentum, everything is same for angular momentum, but just the calculations are different, right? So for angular momentum, we need to just be assured that we are very much advanced in our calculations or very much good in our maths. Other than that, all the concepts will be covered under the linear momentum concept. So this was the topic list for momentum. There are in unit 4, there are 4 topics. First one is momentum including circular motion. In total, this topic will be named further mechanics. And then after further mechanics, you have electric and magnetic field. And after electric and magnetic fields, we have nuclear physics. Okay. So now all these 4 topics will be explained in detail and obviously using worksheets and everything. The worksheets are not included in this topic list. This is just are the list of topics that we will be understanding in this entire concept. So this was the topic list just for momentum. I will be uploading every topic list for every chapter with the start of those chapters. This is the first PDF for momentum. I mean, you guys will get written PDFs like this, and including with this another class slides. Class slides include that all the things that I will write on the screen to explain you a different topic. Those class slides will also be uploaded. Obviously, every class recordings are recorded in this course, but the problem over here is that the class recordings that I provide using this device, screen recording app, it takes a lot while for the recordings to be loaded for these days. I don't know why, maybe because of internet problem or something. So we have to make a few changes, and that would be this time. I will like download the class recordings in a Google Drive and then share the class recordings in a PDF format. And Adi already knows that I usually make a PDF file for all the class lists in our entire course and make a PDF of that. For example, if I go to my ongoing another A2 batch, that is the October A2 batch, this is the class list for Unit 4 for them. Right, this is how you can get every class list under one PDF, like class video and class slides. And if there is any notes involved in that class, that will also be added in this PDF. So it just makes easier for everyone to get access to every class recording and every PDF or every class slides that was shared in the classroom. This is our classroom. We have uploaded few things. After today's class, we will upload today's class slide and class recordings in this folder. So for every topic, there will be like two folder, one for the PDF notes and another for the class slides and class recordings. And another will be in an assignment format. I will be uploading a worksheet and you have to submit your worksheet in that PDF format. So let's start our classes today. We'll turn off the recording over here and start the classes in the other device. Since we're starting with momentum, and we have also studied momentum in our IGCSEs and in our AS, right? Only about the linear momentum calculations. In AS, we did some angular calculations for momentum, but not that much of a very trickier the ones that we are going to see in our A2 syllabus. In our IGC, sorry, in our AS, we did solve a few momentum questions that involved angles, but the concepts were not that much tricky and like twisted, like the concept that you will be facing in your A2. Other than that, there's nothing actually new to explain in momentum. Can anyone please tell me that what is the definition for momentum? Also, since everyone is from different places, you guys can speak in any language you are comfortable with. For Adi, you have to speak English. I do not understand any other languages. Also, Adi, your mic is not maybe working because there is no option for you to like mute or unmute yourself.
Now can you hear me?
Yeah, I can hear you.
Ah, okay, okay.
So, what is the definition for moment or anything that comes to your mind whenever you see moment?
Is like quantity or motion, right?
Yeah, quantity of motion, and other than that, I mean, speed, velocity, accelerations are also quantities of motion, right? But what is the difference for momentum? Now, if you focus on a journey at first, for example, you are starting your journey along the straight line. We are starting with linear momentum first. Like I will explain all the concepts using the linear momentum concepts first, and then use those same concepts using the angular momentum also. So at first we are only focusing on linear momentum. So now over here, this is a straight line, and this is point A, starting point. This is point B, your ending point. So if your object is at point A, maybe at time zero, it indicates time zero indicates that this is the start of the journey. So at the start of the journey, the object was at point A and its velocity was maybe 10. The initial velocity of this object was 10. So U was 10 m slash s. And now with time, object has changed its position from point A to a different point B, and its velocity has also changed this time. And the time it took for the object to travel from point A to point B was maybe 4 seconds. And the velocity at point B, the final velocity would be 25 meters per second. Now, if I want you to explain that how is the object changing its motion, you obviously calculate the overall acceleration, right? Because you can clearly see that over here, the velocity is not constant. In your IGCSEs and AS, you saw equations like v equals to d by t, and then a equals to s equals to ut plus half at square. Then v square u square plus 2as. Then s equals to u plus v over 2t. And then finally, fourth one would be v equals to u plus at. Now, Saba, can you please tell me that what are the conditions for all these five equations? Like, or assumptions. Like, there was some assumption for all these equations. What was the assumption for this first equation?
That
Sorry, couldn't hear you.
I don't know, sorry.
Okay. Adi, can you tell me what is the assumption for this first equation?
It's like the average velocity. It's not in a precise time.
No, it's obviously an average velocity in a precise time, but what does average actually we're trying to mean by using the word average? Like the gross overall in general velocity, right? Or you can also consider that this equation can only be used in situations when the object is moving with constant velocity. But we cannot use these equations when the object is moving with changing velocity. In this example, you can clearly see that the object is not at constant velocity, right? The object's velocity is continuously changing. Initially, its velocity was 10. Finally, its velocity was 25. So, we can clearly see the object was not moving with constant velocity. And this equation was only be able to be used only when the object was moving with constant velocity. So Saba, can we use this equation to calculate the motion of this object along this journey?
No.
No, because the object is not moving with constant velocity. Now moving to the other four equations. These four equations are usually referred as equations of motions or constant acceleration equations. I would prefer that you people memorize these four equations as constant acceleration equations, because that way you can understand that in which situations or in which scenarios you're supposed to use these equations for. So these equations are only for constant accelerations equation. Now, what does constant acceleration mean? It means that acceleration is staying the same, or the value for acceleration, rate for acceleration is same for the entire journey. But does constant acceleration mean constant velocity, changing velocity, or decreasing velocity? Can anyone tell me what does constant acceleration mean about velocity?
Like it means that this velocity increases by the same amount, like each
Right.
interval.
Right. It means that velocity is increasing by the same amount in each interval. For example, if I draw three cars, just for simplicity, maybe every car is 1 centimeters apart. This is not exactly every car. This is just a situation of one car in three different positions after 1 second. Okay. Like this is just the same car, but after exactly 1 second, it's changing its position from A to B to C. Then it's labeled A, B, C. If the acceleration for the car in every three situations are like 5, it actually means that if the velocity of the car at point A was 15, then the velocity of the car at B would be 20. And the velocity of the car at C would be 25. Acceleration, if you focus on the unit for acceleration, it means meter per second square, which can be broken down as m/s over s, which means the velocity would be increasing in each second, the amount of velocity that would be increasing in each second. So over here, if the acceleration's value is 5, it indicates that the velocity would increase by 5 meters per second in each second. Right, so A equals to 5 m/s square actually indicates velocity would increase by 5 meters per second in each second. So in this scenario, we are going to assume that the object is moving with maybe constant acceleration. So now if we have to find out the amount of force that was being acting on the particle for the entire journey, what you have to do, you have to consider the entire journey as a whole. You can't find out the amount of force, or you can't find out the momentum at one exact point. I mean, if you have to find out the acceleration for this journey, what is the equation that we're supposed to use? We are going to use A equals to V minus U over T. That kind of takes the start of the journey and the end of the journey, right? So you're taking just the average of the acceleration, or the acceleration for the entire journey. You cannot focus on one moment while the object is moving or rolling across the floor, right? If you have to find out the force, you have to focus on the entire journey as a whole. So that's the limitations for force. If you focus on that what amount of force or what amount of changes was occurring on the object at one exact moment, that is the calculation for momentum, right? For example, for force, you have to use F equals to ma, right? Mass is constant for that specific object, but acceleration takes this entire journey as a whole. It gives you a gross value, like an average value. But if you want to find out the changes in the motion of the particle in one moment, you can use its mass and velocity at that exact moment to find out momentum. So difference between force and momentum is force gives you an actual idea for the entire journey, overall journey, whereas momentum gives you the change in motion that is happening to the ball as it is moving across its entire pathway at that exact moment. So momentum, let me just write this in symbols. M is equals to mv. The only difference is for force, you are using acceleration. For momentum, you're just focusing on one exact point using velocity. Is the difference clear between force and momentum? Any questions till now? Okay, I think that it's quite easy for Adi to cope up with me, but for Saba, are you not like clear with the concepts of acceleration, constant acceleration, or uniform accelerations?
Yes, it's clear.
No, I mean, I'm asking that if you have any problems from the like basics of acceleration, velocity, and
No, I have no problem.
no problem with that. Like, if you have any problems, then you can ask. Okay. Okay, then let's move to momentum. This was just the difference between the we have understood that what exactly force is from our IGCSEs and AS, but understanding momentum was very difficult because everyone was just giving me the definition that it is a product of mass and velocity, nothing else. But if you actually go to the like quantum physics level, I mean, we will actually go to the quantum physics level in A2, and it would be much more clear if we are like after explaining the quantum physics. Momentum is a very important topic in our quantum physics conservation also. So difference between force and momentum. One last time I'm saying this. Force is like the average change in motion for an object. Momentum is the instantaneous change in motion for that object. So now let's focus on the overall same concept, definitions, or what kind of quantity is it. Now, momentum from the equation, I mean, we did use dot multiplications. Dot multiplication is just a calculation that we can use to identify if a certain quantity is scalar or vector. Again, that is not included in our syllabus, but I use it to explain, like, it's much easier for me to understand if a quantity is scalar or vector by explanation than by memorizing it. So I'll just introduce dot multiplication over here again. Scalars are considered with like assigned with plus sign, and all the vector quantities are assigned with minus sign. So if you have to understand that if momentum is a scalar or vector, we have to use its equation. Momentum is represented with P, mass, and velocity. Mass is a scalar, velocity is a vector. And if you find the product of plus and minus, you finally end up with minus. That means the final sign for momentum is minus. Minus was an indication for vector quantities, indicating that momentum is a vector quantities. Now again, since it is a vector quantity, it will have both parts, magnitude and direction. Now, if an object is moving with constant velocity or constant momentum but changing its direction, then we would say that the object's momentum was also changing because we're not only focusing on the magnitude of the momentum, we're also going to focus on the direction of the momentum here because it is a vector quantity. The unit over here would be, since we have the product of like momentum is the product of mass and velocity, so it will be mass into velocity, which is kg m/s, or you can also use gram centimeter per second. Kg m/s is the SI unit. Other than that, you can use like multiple units that are available. Gram centimeter per second. This is the SI unit. So this is a vector quantity. This is the like SI unit and normal units for momentum. Now let's list down that what types of momentum we are going to consider in our AS. Sorry, A2. So momentum has types of objects, like how many objects we are going to work with in momentum, and types of directions. First one is one object, you're working with one object. Another is you might work with two objects. Types of direction is linear momentum and angular momentum. Or you can also say that as two-dimensional momentum because you have to use the cost component and sign component. So that can also be said as one-dimensional, two-dimensional. So angular momentum. 1D, or you can also consider this as 2D. So now the overall basics are completely done. So let's just move to our first mini example for momentum. I was already using that example in part, like in the previous part. Like this is option like point A, this is point B. At time t equals to 0, its velocity was 10 meters per second, right? And final velocity was 25 meters per second. And the time it took for the entire journey to be traveled was 4 seconds. Now, if you have to find out the momentum, you can find out the moment at point B and momentum at point A separately. For example, momentum at point A is mass into velocity. Maybe the mass of the entire object is 2 kg. The entire equation would be mv, which is 2 into 10, which becomes 20 kg meters per second. And doing the same calculations for momentum point B, which is mv and 2 into 25, that is 50 kg meters per second. Right. Now, again, as at this part, we are obviously assuming that every object is moving like one object there is, but it is just continually moving towards right. Right? There are no double directions involved. Whenever we're working with vector quantities where the object is just moving with one direction, we do not have to assign any signs with it. Like for this one, this is an example for vector quantity in one direction. So that's why I'm not writing any momentum towards direction right or left as positive. We do not need to mention any direction as positive since this is an example for single motion. So this was just the basic for the momentum. Now, how to calculate momentum along its entire journey on two different parts. If you want to find out that what is the change in momentum for the entire journey, you can use the equation change in momentum final momentum minus initial momentum. Obviously, PB was the final momentum, PA was the initial momentum. So let me just write it down. Final momentum minus initial momentum. Final momentum was PB minus PA. We calculate this 50 minus 20. So you will get 30 kg meter per second. Now you can clearly see that changing momentum or momentum as a separate concept doesn't have any different unit. They all have the same unit. Change in momentum can also be written as delta V. Another thing that if you want to find out that how the momentum was changing with time, the entire quantity is then named delta t by so delta p by t. So I label like write this quantity at first. Change in momentum with respect to time. Whenever we are comparing one quantity with respect to time, we call that entire situation, like entire sentence as rate of change in momentum. Right? Let me just write it down over here. Rate of change in momentum. Now, mathematically, we can write it down as delta P over T. Now again, this is the equation delta P over T. You can break down delta P in terms of mass and velocity. For example, if you consider that final velocity is V, initial velocity is U, right? So it becomes kind of mv final momentum mass into final velocity minus mu initial momentum mass into initial velocity divided by time. Now again, if you just keep on focusing on this delta P over T, you can clearly see that m is the like common for both the numbers and the numerators. So you can take m common and it will look like v minus u over t. V minus u was acceleration, so you can say delta p over t is equals to ma. And again, ma was the formula for force. So you can finally conclude delta p over t equals to force. Can anyone like tell me the overall Newton's second law definitions? What was Newton's second law?
Second one you said?
Sorry,
The second
Newton.
one?
Yeah, second one.
It was something like uh I don't remember actually.
Okay. Saba, would you like to try?
I know that it's it equals to MA.
That's the thing we all assume that Newton's second law states about F equals to ma. But Newton's second law not only states about F equals to ma. I mean, this was the generalized basic definition or gross idea that we were built to think with the reference of Newton's second law. For example, Newton's first law only gives us a hint about inertia. Newton's third law gives us a hint about action reaction forces. And Newton's second law gives a hint about F equals to ma. But in our A2, we have to focus on the entire sentence. The entire sentence was that Newton's second law states that the rate of change in momentum of a moving object is equal to the force applied. We just write this down over here as N2. Rate of change of momentum is equal to the force applied on that object. So with the reference of force or with the idea of unbalanced force, we were using in like Newton's second law concept, right? But the actual definitions of second law, the meaning of second law was this derivation, the rate of change of momentum with respect to time, like this entire derivation that we did. From this derivation, we can clearly see that rate of change of momentum, the final thing we get at the end of the entire derivation was rate of change of momentum was equal to force. Right? So over here, this was the final definition for your Newton's second law. You have to obviously understand this entire working. I mean, you did this entire working in your IGCSEs or AS. In your A2, it will obviously not play that much of an important role, but you have to might use this in the like star mark questions. You have to use this as a reference for the 6 mark questions. So I would suggest that memorize the Newton's second law and understand the conversion or the relationship between like Newton's second law and your rate of change of momentum. Like how can you derive the equation for force from the rate of change of momentum? Is there any problem so far?
Hmm.
So if there is no problem, then we will solve example questions. I've already uploaded one example questions in the classroom. And after that, we will move into law of conservation of momentum. Before that, let's just go to that ETF first. Sure. We have explained till now, like up to this level, and after that, we will focus on the example one. In example 1, it says that a ball of mass 25 kg hits the floor with a velocity of 2 and rebounds with a velocity of 1 meters per second. The ball is in contact with the ground for zero point 0.1 second. We need to calculate the force that the ground hits on the ball and state and explain the force that the ball exerts on the ground. Now over here, we have to use the concepts of impulse also. So let's first introduce impulse and then come back to this equation. It would be much easier for me to explain this entire concept after we're done explaining impulse. Impulse is a very short concept. I think we did our calculations for impulse in AS. Yeah, we did explain AS, like impulse in AS, but not that much in detail. Can anyone tell me, like, any ideas they have about impulse? Any idea that they have, that you guys have about impulse? Okay, what is collision? Just like tell me the definition of collisions. Sabah, can you turn on your mic and please tell me what is the meaning of collision? Okay, come on.
When two objects collide and act as a single particle.
Yeah, I mean, when two objects are colliding, right? We do not know that in which way they would moving after the collision. It's just meaning that when two objects are kind of coming in contact with each other all of a sudden, that can be considered as a collision. Now, over here, I will explain that originally there was like a stationary ball or something, stationary like wall, and on this wall, I threw a tennis ball or something on that wall. So this ball came in contact with this wall for a certain time and then rebounded back. So what happens during the collision is that this can be explained in terms of Newton's third law, Newton's second law, moment concepts in three different ways. So let's focus on this very clearly. When the ball come in contact with this wall, obviously by throwing this ball, throw means that I am projecting this ball with an force. Otherwise, it won't be moving in this way. So I am throwing this ball with an initial force. So when it comes in contact with the wall, there are two forces acting on each other. The first one is a force, like normal reaction force from the surface of the wall on the ball. This is a like force from the surface of the wall on the ball. So let me just consider F wall because wall was the origin of this force. And now, according to Newton's third law, there will be also a force acting on the wall but in the opposite direction of the same magnitude. So over here, another force from the ball to the wall of the same magnitude but in the opposite direction, indicating the Newton's third law of motion. So now if you draw this like over here, it will be FB, force from the ball on the wall. Now again, if you focus on this one, initially the mass object's velocity was something like 20, 30, 40, doesn't matter. But after this collision, what happens is that there was an extra force of F.W. Newton was applied on the ball. And because of this force, we know for the time being that if a force is being applied according to Newton's second law, acceleration will also change. And again, acceleration is directly proportional to velocity. If the acceleration is changing, the velocity would also change. So this entire part, what happens is that if you focus on the final and initial velocity, you would just be focusing on that Originally, the mass was m. After the collision, the mass is still m. Or initially, the mass, like initial velocity was maybe 10. After velocity, maybe it is 25. Now, why does the velocity increase after collision? Because of this Fw force being acted on the object. There is no other reason why the object's velocity would increase after the journey, or why the object's like velocity is supposed to increase after a collision or might decrease after a collision. That's only because of the presence of Fw force. The force that they experience from the other surface during collision causes them to change their velocity. And because of this, they have different before and after collision velocity. Sorry. Now, this force was only applied on the object while it is in contact. This kind of force that are being applied on each other during momentum collisions are contact forces. Like the forces, like the objects must be in contact, otherwise the forces cannot play any role on the other object. So the forces are contact forces. So if the ball is in contact with the wall for maybe 2 seconds, then for those 2 seconds, the Fw meter was acting on the ball. As soon as the object moves away from the ball or becomes contactless with the wall, the Fw cannot act on this ball. Right? So you can change, like, impulse is a concept for change in momentum also, and also in terms of force and time. Change in momentum, as in that impulse explains that how the momentum was changing before and after collision. And also, your impulse also explains that in which way or how much force was being applied on the object for how long time. So impulse can be calculated in two different ways. I is calculated in two different ways. First one is change in velocity, change in momentum. That's delta P, which is mv minus mu. And according to this way, your final unit for impulse should be, right, kg meters per second, right? Nothing different for this situation. But if we are using F into T, F into T means force into time. Then your equation changes. Force is Newton, time is seconds. But they really doesn't mean any different quantities. For example, if you break down force, is kg meter per second square into second. Now, okay, second square can be further broken down as fractions as kg second square into second. These seconds get cancelled out and are lifted. Kg meter per second or kg meter per second. But you can clearly see that either way, the unit is still the same, kg meter per second. Even if you use the equation with force into time or use the equation with mv minus mu. Now, this was the overall concept for, wait, let me just keep it again. This was the overall concept for impulse. Impulse basically indicates that for how long time, what amount of force was being applied on the object during the collision. We can express momentum, the impulse, in changing momentum concept or in forces concept. Either way is accepted. So now moving to that question that we were working with. Now, let me just tell this again that even if you use changing momentum or force into time, impulse is a vector quantity, right? If you use dot multiplication or anything, you can understand that using force into time, force was a minus, time was a plus. Product of minus and plus would be finally minus, indicating that impulse is also a vector quantity. It doesn't have any different unit. The unit is still the same, kg per meter cube. So let's just go to that question again and let's try solving this time. Over here it says that a ball of mass 0.25 kg hits the ground with a velocity of 2 and rebounds with a velocity of 1. The ball is in contact with the ground for 0.1. We need to calculate the force the ground exerts on the ball, and we have to explain the force that, explain the force that the ball exerts on the ground. So let me just first draw a diagram for this entire slide, then start solving it. Wait, mass was 0.25, speed was 2, final speed was 1, rebounding speed was 1, and in contact with the ground was 0.1 second. Wants to find out the force. and we have to state and explain the force that the ball exerts on the ground. So the overall scenario was that there was a ground, a ball was falling to the ground with a velocity of 2 meters per second. And after being in contact with the ground, it was rebound from the ground, and it rebound from the ground at a velocity of 1 meters per second. And it hit the ground with a velocity of 2 meters per second. So we can clearly see that this is an example for kind of double motion, right? Initially, the object was falling downward. Finally, the object was moving upward. And we can also say that initial velocity was 2, final velocity was 1. So if you have to find out the amount of force that was being applied on the ball by the ground, we can clearly see that since the ball hit the ground, there was a downward force provided by the ball on the ground. And according to Newton's third law, an upward force will also act on it. So over here, there was an upward force from the ground on the ball in the upward direction. We need to find out this force. We can clearly see that this force was being applied on the ball, right? So, because of this force, the ball's velocity changes from 2 to 1. So, we can write this time as we do not have the value for force, but we want to find out the value for force, and we know for the time being that the ball was in contact with the ground for 0.1 seconds. So we can write impulse equals to either mv minus mu, and we can also write impulse equals to force into time. Now these are two equations for impulse. We can clearly substitute them together. Since we do not have the final value for impulse, we can just substitute them into each other and find and like make force the subject of this equation. For example, I'm going to substitute equation 2 into 1. So I will write substitute 2 into 1, which would make everything look like Ft equals to mv minus mu. Now in this scenario, you have to identify one quantity as positive, one quantity as negative. Since we are working with vector quantities in vertical motion, we have from our AS from our AS knowledge, we already know that for the vertical motion, all the vector quantities in the upward direction are considered to be positive, and all the vector quantities in the downward direction are considered to be negative. So we'll consider direction towards up as positive. So let me just write this down. Now force was not given, so you can just change this position for time from the left to right. Mass was 25. Mass was 25 gram maybe. Mass was 0.25 kg, so it will be 0.25. Final velocity was 1, but in the upward direction. Initial velocity was 2 in the downward direction, right? So it will look like 1 minus 2. Right, V minus U. V was uh, V was 1, U was 2, but in the downward direction. That's why 2 has a minus sign in front of it. Divided by the total time taken in the journey, it was 0.1. Can anyone calculate the value for force that was being applied on the ball by the ground?
7.5.
7.5, right? So it is 7.5 newtons. This was the amount of force that was being exerted on the ball by the ground. Now, if you go to the second question, which I don't remember. I just read out the question. It was that state and explain that the force that the ball will exert on the ground. Now we need to explain that what amount of force will be exerted by the ball on the ground. We know for a fact that at this contact level or during rebounding session, we are going to focus on the Newton's third law pin. Can anyone like list down the few points for any two forces to be under Newton's third law? Anyone remember what are the points that should be matched for any two pairs to be under the Newton's third law?
They should be same type of forces.
They should be
Same type of forces.
the same type of force, right? They should be of equal magnitude, right? Opposite in direction. They should act on two different bodies. And what else? They should always act from one single line, right? They should create one single line. Now, if I focus on this part, the forces that are actually being involved in this part were part B, this was the ground, this was the ball. Now, obviously, they are forming from like they are originating from one single point or what creating one single line, but we are drawing different spaces so that I can explain that from what point they're actually working on which object. So the blue one is from the ground on the ball. So from ground on ball. And this black one is from ball on ground. But now they did not only want you to find out the value for the force from ball on ground, but they also want you to explain the reason. So the value would still be the same, right? The 7.5 Newton will be applied on the ground by the ball. Now, the explanation would be involved with Newton's third law. And that would be that according to Newton's third law, the force of 7.5 Newton that was exerted on the ball by the ground, the same exact amount of force in the opposite direction will be applied on the ground by the ball according to Newton's third law. Right? So you have to also explain that entire concept for this question. So over here, the situation would look like 7.5 Newton it would exert 7.5 Newton in the downward direction on the ground according to Newton's third law. This was the explanation for the concept. So is there any problem till now for the maths in your example one and anything?
No.
So if there is no problem, then please wait. I'm giving you one worksheet. We'll solve that and give me a picture of your work in the class plate. WhatsApp.
I didn't understand which working.
Sorry, which working? No, I'm giving you a classwork. Just give me 1 minute. I'll like give you a question in this part, and you guys need to solve that, and then take a picture of that like solving maths problem, and send it that picture to me in WhatsApp. We solved these three parts, and the mass of the ball was maybe like 5 kg. Okay, so we just write this down as a gradient. Mass of the ball is 5 kg. Is done solving the question. It's been 10 minutes. Any problems you guys are facing? Simple picture from Saba. Adi, are you still solving the question?
Yes, I was stuck.
You got stuck in which part?
I think it's B.
E. The time, so regarding the time the ball was in contact with the wall. So what is your value for option A? Change in momentum.
It's 145.
Sorry,
145.
145. Saba, you did a mistake. You took 18.5 as the initial velocity. It was the force. Initial velocity was 29, right? This was force, this was initial velocity, and this was final velocity, V, F, U. So if you have to find out delta P, change in velocity, option A, the equation was mv minus mu, which obviously you can use as a, like, make m the subject, and the equation would look like m bracket v minus u. That's totally fine. So if I draw the diagram first, the ball first hits the ground, like, so it hits the wall, and then rebounds back in this direction. So we're gonna take the direction towards right or left as positive, depending on our situation. So I'm just taking direction towards right as positive. So direction towards right as positive, which means that our initial velocity would be positive, but final would be negative, right? So over here, it will be 5 minus 48 minus 5 and 29. So if we calculate this, you get minus 385 kg meter per second, which means that the final momentum was greater in the rebounding, like after the rebounding. That's why you have minus 358. So that's not a big deal. This was the final velocity for change in momentum. And after that, like, you can obviously change, right? Write this as 358, 385 kg meters per second. Instead of using the minus sign at the front, you can use this much momentum towards right. So towards left, because we are taking direction towards right as positive, right? So towards left. Sorry, yeah, towards left. The final value came out negative. It means that in the opposite direction, the final momentum was acting. It means that if we are taking direction towards right as positive, your final momentum was greater in the left side or after the rebound. So now they want you to find out the value for B. So now B, it's quite easy. Over here, up to the time being, sorry, for part B, we did the calculations at the very top page. Let me just scroll up to there. Yeah, we can see here that changing rate of change in momentum was equal to force, right? So now we can use that equation to find out an equation for time. The equation was force is equals to delta P over T. We do have the value for force, which was 18.5. If you have to find out the value for T, just make T the subject. Delta P over F, which is 385 minus 18.5. There is no need to write the minus sign in front of the delta P value because it was just there to indicate the direction of the final momentum. So it is 385 divided by 18.5. You get 20.8 seconds. Saba was halfway there. She just made a mistake taking the value for initial velocity. Instead of taking 29, she took 18.5. Okay, so the final time is 20.8 seconds. And again, if you have to find out the value for, they want you to find out the value for delta P over T, right? Calculate delta P over T. You do not need to do any calculations. We know for the time being that rate of change in momentum is equals to force, right? So if force was 18.5, there is no point of doing calculations. This was just a conceptual question that so if force is 18.5, then rate of change of momentum will also be changed like 18.5, the same value. No need to do any calculations. You can just simply write delta P would be 18.5 Newton. Or since we're working with delta P rate of change of time, you can just consider kg meter per second by second. That would also be seen. Eventually, it would mean the same unit, kg meter per second square or Newton, but still I'm just writing this as a like broken format. Is this classwork clear enough for everyone to understand?
Yes.
So if this is clear, we are going to stop our class over here, but we will have a small classwork, like normal homework, because we have another class tomorrow at 10:30 p.m. of our time. So I will post a small class like homework after today's class. You guys need to solve that and send me the picture of your working in the group, not in the personal inbox, in that group. And that will be like be very better if you can send it to me before 8 a.m. tomorrow because my next class would start at 8 a.m. tomorrow.